Around 4 million years ago, the ancestor of humanity, Australopithecus, finally appeared on Earth. Although being called the ancestor of humanity might sound grand, in reality, Australopithecus at that time was nothing more than prey for numerous predators. They were not strong like other animals, couldn't fly like birds, and couldn't swim well like fish. In other words, humans were insignificant animals with nothing particularly outstanding. However, as time passed and humans began to walk on 2 feet, their hidden potential started to reveal itself. In the blink of an eye, humans rose from being prey to predators, and soon they became superior to anything else on Earth. At this point, some scholars began to have questions. If the history of the Earth did not start with the birth of humanity, what existed on Earth before then? Did the Earth also have a moment of birth? If so, what is the nature of the unknown black space that holds the Earth, the universe? These questions have been posed since thousands of years ago and remain a mystery even in the 21st century. Since ancient times, humanity has strived to find the fundamental essence of all things. Serious research began in ancient Greece, a period when all academic disciplines first flourished. Ancient Greece, one of the most prosperous times in human history, enjoyed a relatively affluent lifestyle compared to other eras. Instead of just seeking immediate sustenance, people began to question fundamental issues such as why humans exist and why they make certain choices in specific situations. Their inquiries eventually extended to the universe itself. Many philosophers put forth numerous theories to explain the world more clearly. Around the 6th century BC, Thales, the first philosopher of ancient Greece, sought the fundamental essence of all things. What he discovered was that the fundamental essence of everything was water. He continued discussions on the constituent particles of matter to understand natural phenomena. As a result, Empedocles proposed the theory of the 4 elements for the first time. The theory of the 4 elements posited that all things are made up of water, fire, air, and earth. About 100 years later, Aristotle developed this theory further, asserting that each of the 4 elements possesses the qualities of wetness, dryness, coldness, and hotness. In summary, water is cold and wet, fire is dry and hot, air is wet and hot, and earth is dry and cold. Looking back now, the idea that everything is made up of just 4 elements sounds quite absurd, but considering that this was an era without basic concepts of matter, it was indeed a remarkable insight. Aristotle also believed that each element had a specific weight and thus a designated place. He argued that the most stable state was when the lightest element, fire, was at the top, followed by air, water, and then earth in that order. However, this seemingly perfect theory of the 4 elements had a critical flaw. It couldn't explain the celestial bodies that continuously moved up and down in the sky. If they were made of fire, they should continuously rise, and if they were made of earth, they should continuously fall. The fact that they moved up and down was inexplicable. Eventually, Aristotle posited that there was an unknown element that caused these celestial bodies to move up and down. He named this 5th element ether. This idea naturally led to the development of the geocentric model, which posited that the universe revolves around the Earth. Until the advent of modern astronomy, the geocentric model was a very convincing theory. It wasn't easy to accept the idea that the Earth, on which one stands with both feet, was moving, let alone the sun rising and setting around the Earth. However, there was a significant problem with the notion that all celestial bodies revolved around the Earth. If all celestial bodies were indeed revolving around the Earth, they should always move in a consistent direction, like the sun or the moon. Occasionally, however, some celestial bodies would set in the west from the east and then, at other times, move from west to east, which was quite strange. But the greatest astronomer of the time, Ptolemy, came up with a theory that perfectly explained this phenomenon. The solution was the concept of the epicycle. In simple terms, an epicycle is a theory that suggests a celestial body orbiting the Earth also makes a small circle on its own path for no apparent reason. During the process of making this small circle, there would inevitably be a moment when the direction reverses, making it appear to us as if the celestial body is moving from west to east. This was the appearance of the universe based on Ptolemy's introduction of epicycles. It seemed quite complex. Surprisingly, however, by incorporating epicycles, it was possible to perfectly explain the movements of all celestial bodies observed in the sky at the time. Mathematically, there were no errors to be found. They finally believed they had unraveled the unexplained phenomena of the universe and discovered the laws of all things, leading to the geocentric model being accepted as the absolute truth in cosmology. However, about 14 centuries later, cracks began to appear in the seemingly perfect geocentric model. For approximately 14 centuries, Ptolemy's geocentric model was regarded as the truth of cosmology, and no one dared to challenge it. In fact, the concept of the heliocentric model, which posits that the Earth moves, existed alongside the geocentric model that suggested the sky moves. As early as the 3rd century BCE, the ancient Greek philosopher Aristarchus had already advocated for the heliocentric model. However, the heliocentric model was not attractive to them. The world was supposed to be governed by simple and clear laws, but the heliocentric model made the depiction of the movements of other planets overly complex and inelegant. But 14 centuries later, the heliocentric model was rediscovered by an astronomer. In the early 16th century, the Polish astronomer Copernicus studied Ptolemy's geocentric model and was amazed at how accurately his theory explained the movements of the sun, moon, and planets. However, something bothered him: the core of Ptolemy's geocentric model, the epicycle. After the telescope was developed, Copernicus used it to observe celestial bodies in the sky and collected data over many years. To explain the movements of these bodies using Ptolemy's epicycles, at least 80 epicycles were needed. While the use of numerous epicycles could somewhat explain the movements, he believed that the universe could not operate in such a complex manner. Moreover, although Ptolemy's model predicted the positions of the planets quite well, there were continuous discrepancies when compared to actual observational data. At the time when Ptolemy proposed the geocentric model, ancient Greek philosophers believed that celestial bodies orbiting the Earth moved in perfect circles at constant speeds. Their interest in the heavens stemmed from their curiosity about celestial bodies moving in circles, so it was natural for them to believe in constant circular motion. Thus, they believed that the sun also orbited the Earth at a constant speed, making the lengths of the 4 seasons always the same. However, measured data showed slight discrepancies. Spring lasted 92.75 days, summer 93.75 days, autumn 89 days, and winter 89.5 days. Ultimately, Copernicus thought that the universe, which should be simple and clear, could not be so complex, and with these discrepancies, he believed it was inconsistent with the harmonious providence of God. Seeking a beautiful cosmological model that aligned with God's will, he developed his own theory. First, he decided to eliminate all of Ptolemy's epicycles, which were both the core and the problem. He then researched what kind of cosmic structure would allow planets to move in perfect uniform motion. As a result, he came up with the extremely shocking idea that all planets, including the Earth, revolve around the sun. This idea is what we know today as the heliocentric model. He realized that the heliocentric theory quite accurately represented the story of the universe, and he developed this idea more concretely, leading to the creation of the book On the Revolutions of the Celestial Spheres. Around 1530, the heliocentric theory was a truly astonishing theory, and once it was revealed to the academic world, it was only a matter of time before he became a famous figure worldwide. However, unfortunately, he could not share this amazing fact with the world. The reason was that the geocentric theory, which had been ingrained in people's minds throughout the 14th century, had a very strong foothold. The geocentric theory, which posited that the Earth was the center, carried the notion that the Earth was an absolute entity, almost like a god. Denying this was tantamount to going against the will of God. Copernicus, being both an astronomer and a devout Christian, found it difficult to reveal this theory to the world. About 40 years later, just before he passed away, this book was finally made public. Naturally, his heliocentric theory was not accepted by the academic world, as it was considered blasphemous, and it was even treated as a banned book. The persecution of the heliocentric theory was quite severe. In the late 16th century, Giordano Bruno was greatly inspired by Copernicus's heliocentric theory. Furthermore, he made a very futuristic claim that the Earth orbits the Sun, and the stars in the night sky are individual suns far away, around which planets like Earth are revolving. Therefore, he argued that it was only natural that many universes existed, and Earth could not be the center of this universe. Up to this point, it was just an opinion, and as long as he didn't boast about it openly, it wasn't a big problem. But when he accidentally mentioned these heretical ideas to a noble while working as a tutor in Venice, things took a turn for the worse. The noble, upon hearing this, immediately sent him to the Inquisition, and he was eventually burned at the stake for his heretical statements. Thus, advocating for the heliocentric theory in the academic world at that time was extremely dangerous, to the point of threatening one's life. However, around that time, there was a great scientist who dared to advocate for the heliocentric theory, despite the risks, the famous Galileo Galilei. He was very curious about astronomy at the time, and was looking at the sky through a telescope. In doing so, he discovered 4 celestial bodies that appeared to be satellites of Jupiter. This discovery alone was sufficient to gain recognition in the academic world, but the problem was that these satellites were orbiting Jupiter, not Earth. Not only did they observe the Moon and discover that it too was a rocky celestial body, no different from Earth, but by observing the movement of sunspots, they shattered Aristotle's cosmology, which stated that celestial bodies were perfect and fixed. Additionally, they crucially found a fatal flaw in the geocentric model. According to Ptolemy's geocentric model, Venus, which orbits closer to Earth than the Sun, could never hide behind the Sun. Therefore, we should never have been able to see a fully illuminated Venus, like a full moon, because the intense sunlight would obscure it. However, strangely enough, we were able to see a fully illuminated Venus, which proved that Ptolemy's geocentric model was incorrect. Besides this, Galileo Galilei discovered numerous pieces of evidence refuting the geocentric model, and eventually, in 1609, he began advocating heliocentrism. Initially, he did not face severe criticism due to his scholarly reputation and career, but his relentless insistence on heliocentrism eventually made him unpopular. Thus, in 1616, the religious trial he had avoided for 7 years finally came upon him. Fortunately, the trial was not as cruel as we might think. The inquisitor Roberto Bellarmino politely requested evidence for heliocentrism from Galileo. However, Galileo had only found evidence that Ptolemy's geocentric model was wrong, and had no proof that heliocentrism was correct. Consequently, he lost the trial. At this time, Copernicus's book, On the Revolutions of the Celestial Spheres, became a banned book. However, the suppression of heliocentrism could not quell the curiosity of scientists. In the early 1600s, Johannes Kepler, a German mathematician and astronomer, decided to focus particularly on Mars among the numerous celestial bodies. He spent 8 years persistently observing Mars and collected all the data. Using this data, he attempted to describe Mars's orbit. Until then, all astronomers believed that whether the Sun orbited the Earth or the Earth orbited the Sun, the orbit would always be a perfect circle. However, according to Kepler's observations, Mars did not orbit in a perfect circle. After numerous rechecks over several years, he finally came up with the idea of an ellipse. Miraculously, this resolved the long-standing problem of Mars's orbit, and in 1609, he announced this fact to the world in Astronomia Nova, New Astronomy. 7 years later, in 1616, he published Harmonices Mundi, the harmony of the world, presenting Kepler's 3 laws, which are indispensable in the laws of the universe. However, even this was not enough to overthrow the firmly established geocentric model, and time passed by ruthlessly. Soon after, a scientist emerged who would finally topple the geocentric model. His name was Isaac Newton. As you know, Newton discovered the universal law of gravitation, which states that objects with mass attract each other. This universal gravitation successfully explained why the Earth could orbit the Sun, finally toppling the geocentric model that had dominated humanity for 14 centuries. Subsequently, James Bradley discovered the phenomenon of stellar aberration, where starlight appears tilted due to the Earth's orbit, supporting heliocentrism. In 1838, astronomer Friedrich Bessel discovered stellar parallax, where the same star appears differently depending on the observer's position, providing decisive evidence that the Earth orbits the Sun. Thus, the cosmology that began in the 6th century BCE finally concluded with heliocentrism over 2,000 years later. However, this only revealed the relationship between the Earth, the Sun, and the other planets, leaving their origins still unknown. Yet, about 100 years later, the greatest genius in human history would be born, who would solve even this mystery. In 1905, Einstein gained worldwide fame by publishing his theories on the photoelectric effect, Brownian motion, and special relativity. The three papers he released during this period were groundbreaking discoveries that formed the foundation of modern science, making 1905 known as the Miracle Year. But Einstein did not stop there. In 1915, he published a historic paper that sought to uncover the fundamental nature of the universe, or rather, the fundamental nature of everything. Yes, it was the general theory of relativity. Among the vast amount of information contained in this theory, the most important was the equation known as the Einstein field equations. This equation allowed for the calculation of the curvature of space-time based on the distribution of matter, offering an ultimate equation to uncover the fundamental nature of everything humanity had been seeking for ages. If one could fully solve this equation, it would provide access to the essence of the world that had plagued humanity for thousands of years, and even explain why and how the universe was born. However, Einstein arrived at a slightly incorrect conclusion with this equation. At that time, scientists believed that the universe had always been, and would always remain unchanged, maintaining its current form for millions and billions of years. It seemed like common sense, as looking at the sky today, tomorrow, or even a year from now, one would not easily notice any immediate changes. However, contrary to this common sense, no matter how Einstein tried to interpret his equation, he could not obtain a static universe as a result. But since the prevailing belief was that the universe neither expanded nor contracted, he eventually introduced the famous cosmological constant to correct for this slight discrepancy. In 1917, using this, he published the paper Cosmological Considerations in the General Theory of Relativity, bringing him a step closer to the fundamental nature of the universe. However, in 1927, a Belgian scholar named Georges Lemaitre concluded that according to Einstein's equations, the universe must be expanding. But at a conference in Brussels the same year, after hearing Lemaitre's presentation, Einstein remarked, "Your calculations are correct, but your physics is abominable." Thus Lemaitre, who was still a novice in the academic world, seemed to be dismissed by Einstein's disdain. However, in 1929, an astonishing observation by American astronomer Edwin Hubble, who was observing celestial bodies, discovered that the objects he was observing were moving away from him. The fact that celestial bodies were moving away could only be explained by the expansion of the universe. This moment validated the idea proposed by Lemaitre in 1927 through observational evidence. Consequently, Einstein had no choice but to retract his static universe theory and the cosmological constant. But what Lemaitre had actually intended to convey was not just that the universe was expanding, but that if time were reversed, the universe would have contracted, and ultimately, if rewound far enough, the universe would have started from a single point. This is what we now call the Big Bang. However, while the expanding universe could be accepted as an observational fact, the notion that this vast universe originated from an inexplicable explosion from a single point was hard to believe. Questions arose about what could have caused such an explosion, and how powerful it must have been to create such a universe. The Big Bang theory was so revolutionary that it was hard for scientists, who had believed in an unchanging universe, to accept. As a result, some scientists who could not accept the Big Bang theory acknowledged the expansion of the universe, but could not accept that it started with a Big Bang. They proposed the steady state theory, where the universe expands. But to fill the expanding vacuum, extremely small amounts of hydrogen atoms, undetectable by humans, are spontaneously created. This idea seemed absurd, ignoring the law of conservation of mass, but it underscored their inability to accept the Big Bang theory. However, in 1964, while observing the universe at Bell Labs, astronomers Arno Penzias and Robert Wilson encountered a strange noise in their detector. Initially, they thought it was due to dust or birds interfering with the signal. But even after eliminating all variables, the noise persisted. This noise was actually the cosmic microwave background radiation, uniformly spread in all directions in the universe. This provided clear evidence that the early universe, following the Big Bang, was extremely hot, around 3,000 degrees, and that matter was distributed in a highly uniform state without the formation of galaxies or stars. Thus, the long quest to understand the essence of the universe was finally realized. But what exactly was the Big Bang, which is considered the essence of the universe? What happened immediately after the Big Bang? And how did a highly dense point create this vast universe? 100 years ago, we finally discovered the secret of the universe, the Big Bang. Until then, it was believed that the universe was eternal and perfect, and such a perfect universe was thought to be God itself. However, as science developed, we realized that there is no God who orchestrates everything in the world. Nevertheless, if God exists, it was thought that this God would be a transcendent being who created the universe. Perhaps because of this, scientists have been desperately trying to uncover the secrets of the universe that gave birth to us humans. And finally, they reached the point of discovering that the beginning was the Big Bang. So, what exactly happened after the Big Bang? How did the universe begin? Feel free to ask if you need any further assistance. The most powerful explosion in the history of the universe that started from a single point, the Big Bang. However, this explosion was not like the explosion of a bomb, as we might think. The explosion referred to in the Big Bang was not strictly speaking an explosion, but merely the phenomenon of the universe expanding in size. Therefore, the expression that the Big Bang happened at a single point is actually incorrect. Before the Big Bang, there was neither time, space, nor dimensions that could be called a point. Thus, the question of what existed before the Big Bang is flawed from the premise. But for convenience, let's start by assuming the Big Bang was an explosion that occurred at a single point. Right after the Big Bang, space began to emerge suddenly, and all particles began to move away from each other to fill the newly created space. At this moment, the temperature of the universe, which had just exploded and held immense energy, was a staggering 1.5 trillion Kelvin. This temperature was unimaginably high, roughly 100,000 times the core temperature of the Sun, which is about 15 million degrees. At such an extremely high temperature, all particles would start to move wildly due to the overwhelming energy, making it impossible for current science to explain what happened at that time. Considering that the target temperature for our current nuclear fusion projects is 100 million degrees, we can grasp how extraordinarily high 1.5 trillion K is. However, if this temperature dropped to around 100 billion K, it would be possible to predict what might have been happening in the universe at that time. So, how long did it take for the universe at 1.5 trillion K to cool down to about 100 billion K? Surprisingly, it took only 0.01 seconds. At that time, the entire universe was only about 4 light-years in size, and even after filling all of it with energy, the remaining temperature was 100 billion K. In this era, the universe was in an ultra-high temperature state where even atomic nuclei could not survive, and only positrons, electrons, neutrinos, photons, and radiation energy existed. Among these, electrons were the ones we know, the negatively charged particles surrounding atomic nuclei. And in the early universe, there were countless numbers of them. There were also many positrons, which were particles identical to electrons in every way, except that they had a +1 charge. Today, positrons are very rare and can only be observed in laboratory nuclear reactions or supernova explosions in space. But back then, they were so abundant that they were spread throughout the entire universe along with electrons. The next material that filled the universe was neutrinos, which were mysterious particles that only interacted via the weak force and gravity and did not interact with other materials. Not interacting means, simply put, that no matter what material was in front of these neutrinos, they would pass through as if nothing was there. Lastly, there was a vast amount of light, or photons, which unlike the previous 3 materials, had no charge or mass but only carried energy. These particles collided countless times at unimaginably high temperatures, repeatedly undergoing processes of creation and annihilation, and eventually reached a state of thermal equilibrium where the amount of heat exchanged was equal. During this period, the fundamental particles of matter, quarks and gluons, finally appeared. Quarks are the most basic particles of all matter, If the phone or computer you are watching this video on is made up of various metals, those metals are made up of countless atoms. And those atoms consist of protons and neutrons, which in turn are made up of quarks. And gluons are, simply put, the adhesive that binds protons and neutrons, the assemblages of quarks. This indicated that something material was beginning to form in the universe. However, unfortunately, the basic particles of matter, protons and neutrons, were very scarce in the universe at that time. Roughly speaking, if there were 10 billion photons, neutrinos, electrons, and positrons in the universe, there was only about 1 proton and neutron. But as time passed, that ratio slowly began to rise. Thus, 0.11 seconds after the Big Bang, the temperature of the universe, which had been 100 billion K, dropped to 30 billion K. Most of the universe was still occupied by electrons, positrons, photons, and neutrinos, and the number of protons and neutrons was still sparse. However, during this period, the universe underwent a period of dramatic change. As the temperature dropped to 30 billion K, a phenomenon occurred where neutrons and protons converted back and forth into each other. Heavier neutrons turned into lighter protons, and vice versa. This process repeated, and as the temperature of the universe gradually decreased, the relatively heavier neutrons became less active and converted more into the lighter, more active protons. At this time, the ratio of protons to neutrons was 62% to 38%, respectively, and over a long period. This started to form the foundation of the universe. Then, 1 second after the Big Bang, the temperature of the universe dropped from 1.5 trillion K to 10 billion K in just 1 second. As the universe expanded and the temperature dropped, the activity of matter decreased, and changes gradually diminished. However, protons and neutrons continued to switch roles, and at that time, the ratio of protons to neutrons was 76% to 24%. 14 seconds after the Big Bang, the temperature of the universe reached a relatively low 3 billion K, and the early structure of the universe began to take shape. Usually, applying high pressure to a gas can turn it into a liquid, like liquid nitrogen, which we can see around us. However, no matter how high the pressure, if the temperature is too high, the gas cannot turn into a liquid. This threshold temperature is called the critical temperature. If the temperature is above this critical temperature, no matter how much it is compressed, there is no change in the state of the material. Only when the temperature is below this critical temperature can the state change occur. Each material has a different critical temperature, and this period was when the universe reached the critical temperature for electrons. As the temperature of the universe reached the critical temperature for electrons, electrons began to annihilate rapidly. During the annihilation process, energy was released according to E equals mc cc2, temporarily slowing down the cooling rate of the universe. As time passed and the temperature of the universe decreased, the universe began to build up to its current state. It was the perfect time for helium to be formed. Though one might think that the high temperature and pressure of the universe would make helium formation easy, the universe was expanding at an unimaginable rate, making it impossible for particles to meet and undergo nuclear fusion. Instead, protons and neutrons wandering the universe collided quickly and formed helium by chance. In simple terms, when 2 protons and 1 neutron collided, helium-3, He3, was formed. And when 1 proton and 2 neutrons collided, tritium, H3, was formed. When another neutron collided with helium-3, the first helium nucleus we know, with 2 protons and 2 neutrons, was finally formed. This process lasted about 3 minutes, and 3 minutes and 46 seconds after the Big Bang, the universe reached a relatively cool 900 million K. 900 million K was a good condition for nucleosynthesis to occur. Numerous protons and neutrons in the universe began to undergo nucleosynthesis in earnest, creating hydrogen and helium, thus laying the foundation of the universe. The ratio of hydrogen to helium created at this time was about 3:1, and surprisingly, the current ratio of hydrogen to helium in the universe is also 3:1. This, along with the cosmic microwave background radiation, is strong evidence that this universe was born from the Big Bang. After countless nucleosynthesis, the universe began to fill with hydrogen and helium, a process that lasted for tens of thousands of years, eventually reaching a temperature of about 2.725 K. Thus, the long and arduous journey of the Big Bang finally came to an end. Now, the hydrogen and helium born from the Big Bang began to fill this vast universe. The hydrogen and helium, evenly distributed throughout the universe, were drawn together by their own mass due to gravity, forming higher-numbered elements, rock masses, stars, galaxies, and so on. Countless stars were born and died, and about 9.2 billion years later, our Sun and Earth appeared in this universe. Even after that, the universe continued to actively form stars, and about 4.6 billion years later, humans appeared on Earth, striving to unravel the secrets of this universe. However, there were some strange aspects to the Big Bang, which holds all the secrets of the universe. In 1915, the story of the universe was born based on Einstein's general theory of relativity, the Big Bang theory. However, like all the theories that changed the paradigm of their time, the Big Bang theory faced fierce opposition from all directions from the moment it was announced, taking decades to be accepted as the established theory in academia. This wasn't simply because scientists were being stubborn or lacked knowledge, but because there were many strange aspects to the Big Bang theory. After the announcement of the general theory of relativity in 1915, which changed the paradigm of modern science, Einstein was constantly thinking about the universe every day. When researching his masterpiece, The General Theory of Relativity, he found that the story of the universe was very different, or rather, strange, from what he had imagined. According to the General Theory of Relativity, all objects with mass should each have their own gravity. This is an obvious fact. However, the problem was that the numerous celestial bodies in this universe all had astronomical masses, which means they all had enormous gravity. Gravity is an immense force that cannot be ignored, and no matter how far apart objects are, gravity can never be zero in this universe. Although the force of gravity is inversely proportional to the square of the distance, it can never be zero because there is no negative gravity. Therefore, all celestial bodies should be drawn to each other's gravity, causing the universe to contract, since there was no way Einstein's general theory of relativity could be wrong. So, if the universe was indeed contracting due to the immense gravity as suggested by the general theory of relativity, it should have rapidly contracted to reach the state of the Big Bang. However, the universe did not show signs of contraction. Instead, it appeared to be in a calm state. Therefore, in 1917, 2 years later, Einstein proposed a static universe, ignoring the fact that the universe could change according to the general theory of relativity. But as you know, in 1927, the Belgian astronomer Georges Lemaitre discovered that the universe was expanding based on Einstein's equations. This raises a question. According to Einstein's general theory of relativity, each celestial body must have immense gravity. Yet, for some unknown reason, the universe is expanding. Let's assume that this expanding force is strong enough to overcome gravity. Even with this assumption, there were still problems with the Big Bang. If the expanding force was strong enough to ignore interstellar gravity, it could prevent the universe from contracting. But this would also mean that celestial bodies could never get close to each other. In that case, could celestial bodies exist in this universe? According to hundreds of years of scientific research, all celestial bodies in the universe are formed by space dust and gas clumping together under their own gravity. If the expanding force significantly exceeded gravity, these materials would disperse before forming celestial bodies. The Earth we live on, the sun that shines on us, and all celestial bodies in the universe would never have been born. This means that if the expansion speed was too slow, the universe would rapidly return to the state of the Big Bang due to the gravity of all celestial bodies. Conversely, if the expansion speed was too fast, materials would scatter without forming celestial bodies. In summary, for the universe, which has a history of 13.8 billion years, to maintain its current state, it had to have exactly the right expansion speed. This wasn't the only thing that needed to be just right. The Big Bang Theory, initiated by Einstein, Lemaitre, and Hubble, was completed by NASA's WMAP probe launched in 2003. WMAP provided strong evidence for the Big Bang by capturing the state of the universe 380 years after the Big Bang, showing that the universe was evenly distributed right after the Big Bang. This discovery revealed that the universe was surprisingly uniform. However, This finding also raised more questions about the Big Bang. How could the universe be so uniform? If there had been even a slight unevenness, areas with dense celestial bodies would have had immense gravity according to the general theory of relativity. These areas would have eventually developed into black holes if they exceeded the limit mass and gravity, leading to a universe filled with black holes. However, celestial bodies were designed to have only indirect effects on each other, avoiding a universe dominated by large black holes. Looking up at the sky, the seemingly chaotic universe is actually very uniform. How did this happen? Was it divine intervention that designed this uniform universe? Fortunately, this question about the Big Bang could be explained by one theory. That famous theory is the inflation theory. In the early stages of the Big Bang theory, it was thought that the universe expanded gradually to its current state. However, it turned out that the universe underwent tremendous rapid expansion at the 10-10-10-43 second mark after the Big Bang. The size increased by a factor of 1030. If the universe had expanded slowly at a similar speed, celestial bodies couldn't have been distributed this uniformly. But because the universe expanded by a factor of 1030 in an unperceivably short 10-10^43 second, it had no choice but to become uniformly distributed. Due to this instantaneous expansion, we have a relatively uniform universe, and the residual energy is the cosmic background radiation measured at 2.725 K across the universe. However, this fact brought another question. If the universe underwent rapid inflation and became highly uniform, the early universe must have maintained an adequate distance from each other. However, the problem was that if all the matter in the universe maintained such a perfect balance, celestial bodies like our Earth could never have been formed. Particles in the universe need to collide, break apart, and gather together to form celestial bodies like ours. If the attractive forces were in perfect harmony and the state was too uniform, they wouldn't affect each other, and no celestial bodies could form in this universe. Therefore, the universe had to be uniform, but at the same time, it needed a certain degree of non-uniformity. In 1965, Penzias and Wilson discovered the evenly spread cosmic background radiation as evidence of the Big Bang. But now, the problem was that if the universe was too uniform, celestial bodies like our Earth couldn't form, leading to a troubling situation. In this ironic situation, NASA launched the Cosmic Background Explorer, COBE, in 1992 to observe the cosmic background radiation more precisely. As a result, it was confirmed that the universe, which was thought to be perfectly uniform, actually had some slight irregularities. Later, in 2012, the Wilkinson Microwave Anisotropy Probe was launched for more precise observation, confirming that there were more slight irregularities than previously thought. Finally, in 2013, the European Space Agency launched the Planck satellite, revealing that the universe is incredibly uniform. Yet at the same time, non-uniformity is evenly spread, an ironic situation. Thanks to this harmony of uniformity and non-uniformity, we were able to escape the fate of a universe full of black holes. At the same time, stars like the Sun, planets like Earth, and life forms like humans could be born. In summary, the universe is well explained by the Big Bang, with the right expansion speed that allowed matter to clump together appropriately without collapsing, the rapid inflation of 1030 times in 1043 seconds, and the right non-uniformity for life forms like us to be born. It seems we have somewhat unraveled the secret of the birth of our universe. But if there is a beginning, there must also be an end. How will our universe end? In 1905, with Einstein's theory of relativity, the secret of the universe's birth was finally revealed. Whether he intended it or not, it was discovered that the universe has a beginning. That beginning was so mysterious that we could hardly imagine it. But having a beginning also means there must be an end. Just as humans have a lifespan, celestial bodies like the Earth and the Sun also have lifespans. This implies that the universe that contains them also has a lifespan. When humans reach the end of their lifespan, they can no longer engage in life activities or move. Celestial bodies, when their end approaches, meet a dramatic death in forms such as black holes or explosions. So, what kind of end will the universe, a far more colossal entity, face? In 1915, Einstein published the great theory that explains the laws of the entire universe, the general theory of relativity. As a result, this beautiful equation, the Einstein equation, plays a crucial role in explaining the story of the universe. This equation describes how space bends when matter or energy exists within it. In other words, it can be considered a comprehensive summary that contains everything about general relativity. Within it are terms like the Riemann tensor, Ricci tensor, and energy momentum tensor, filled with unknowns that are difficult for the general public to even conceptualize. But if these unknowns could be simplified or their exact values known, only then could we come closer to the truth of this universe, the foundation of everything. However, the problem was that even Einstein, who presented this beautiful equation to the world, could not find its solution. The reason was not only the human aspect of Einstein being relatively weak in mathematics, but also because the equation itself had a monstrous level of difficulty. The Einstein equation goes beyond equations with one or two unknowns like the first-order or second-order equations we commonly encounter, and contains as many as 16 unknowns in a single equation, making it exponentially more challenging than typical equations. Moreover, this equation is not comprised of simple addition and subtraction that we learn in school, but is interwoven with numerous mathematical concepts such as differentiation and integration, making it nearly impossible to solve without being deeply versed in mathematics. Even after more than 100 years since the birth of this equation, the method to solve such equations has not been particularly clarified, and the best we can do is to substitute all possible values using supercomputers with extremely fast computation speeds. Therefore, even Einstein, who created this beautiful equation, could not solve his own equation, to the point where he worried about whether it could actually be used in real research. However, humanity proved to be more remarkable than expected. After Einstein's announcement of the general theory of relativity, scientists, shocked by the fresh insight, devoted themselves endlessly to solving the Einstein equation to uncover the secrets of the universe. By combining and dismantling this complex formula in various ways, they finally reached the first solution of the Einstein equation. And surprisingly, it took only 1 year. In 1916, just 1 year after Einstein's announcement of the general theory of relativity, German physicist Schwarzschild, who was serving as a soldier during the war with bombs flying overhead, attempted to solve Einstein's equation in a somewhat simplified manner. Since it was practically impossible to solve for the values of the 16 unknowns, he assumed a specific situation where all these unknowns would cancel each other out. Through this solution, he predicted black holes and calculated the size at which an object with a certain mass would become a black hole, or the size of the black hole itself, leading advancements in cosmology. However, this was solved under very specific conditions, and the equation still held many secrets. Therefore, in 1922, Soviet physicist Alexander Friedmann assumed that the universe has no specific direction or difference in matter density on a very large scale. In other words, the universe is homogeneous everywhere, and he decided to solve the equation based on this assumption. After complex calculations, Friedmann finally produced what is known as the Friedmann equation, which determines the shape of the universe. The Friedmann equation talks about how the universe evolves based on its initial conditions, and Friedmann thought of the universe's initial condition as its density. If the mass in a certain space exceeds the critical point, the gravitational force between the matter will be stronger than the force of the universe's expansion, leading to a contracting universe. Conversely, if the mass in a certain space is less than the critical point, the force of the universe's expansion will be stronger than the gravitational force between the matter, leading to an ever-expanding universe. And if the two forces are balanced, it would result in a flat universe. Simply put, depending on the current density of the universe that we actually observe, we can know how the universe is currently unfolding and what its eventual fate will be. Currently, the average energy density of the universe, including dark energy, dark matter, and all atoms, is approximately 10^10^29 GCmN3, which is a very sparse density, equivalent to about 0.3 onions in a cubic meter, compared to the density of stars or our bodies, which is about 1 grams cm3. It is an extremely low level. Now that we have the ability to measure the current density of the universe, we can predict how this universe will evolve in the future. So, what will happen to our universe? After Einstein's publication of the General Theory of Relativity in 1915 and Edwin Hubble's observational evidence of the expanding universe in 1929, the prevailing cosmological model among scientists was the steady-state theory. Of course, 2 years before Hubble, Lemaitre had proposed the Big Bang theory, but the idea that this vast universe originated from a single point with an explosive expansion was difficult for scientists of that time to accept. Nonetheless, since Hubble's observations provided evidence that the universe was indeed expanding, they had to acknowledge this fact. As a result, the steady-state theory, which simply acknowledged that the universe was expanding while maintaining that it was otherwise unchanging, emerged as the dominant cosmological model, replacing Einstein's static universe model. From today's perspective, the steady-state theory had many peculiarities. It couldn't precisely explain why the universe was expanding and merely stated that the universe was expanding for no apparent reason. Additionally, it made the absurd claim that atoms spontaneously appeared in the expanding space, which violated the law of conservation of energy. It might seem astonishing that the intellectuals of that time would entertain such implausible ideas, but the scientists who first heard about the Big Bang theory likely had similar thoughts. They must have questioned how the universe could have expanded from a single point. However, as time passed, scientific technology advanced, and astronomical data accumulated, leading us to accept the Big Bang theory instead of the steady-state theory. Consequently, we now have different thoughts about the end of the universe. This new understanding began with the story of the universe proposed by Friedmann in 1922, known as the Friedmann equations. According to the Friedmann equations, our universe could take on 3 possible forms. The first form occurs when the mass within a specific space exceeds a critical threshold, causing the gravitational force between the matter to become stronger than the force driving the expansion of the universe. If we could observe our universe from the outside, it would appear spherical. The surface area of the sphere is finite and determined by its radius, but because a sphere has no edges or corners, there is no end point. In other words, no matter how far we travel from a starting point, we would never see an end. Yet the space we can move through, the universe, is finite. This type of universe is called a closed universe. The second form occurs when the mass within a specific space is below the critical threshold, causing the force driving the expansion of the universe to be stronger than the gravitational force between the matter. In this scenario, the universe takes on the shape of a saddle, opposite to the spherical shape. This form of the universe has no end, and thus, it is called an open universe. The third form occurs when the gravitational force between the matter and the force driving the expansion of the universe are roughly balanced. In this case, the universe is also an open universe, but it appears relatively flat compared to the saddle shape. Based on these forms, the fate of the universe is determined. First, let's discuss the closed universe. As mentioned earlier, a closed universe is a scenario where the gravitational force between matter is stronger than the force of expansion. In other words, the force trying to contract the universe is greater than the force trying to expand it. As the universe keeps expanding, at some point, the force of expansion and the gravitational force due to the total mass of the universe will reach equilibrium. Once this brief moment passes, the universe will start contracting instead of expanding. As a result, the distances between celestial bodies will gradually decrease. As these distances decrease, the gravitational forces between these bodies will increase, leading to a faster contraction. Thus, the previously expanding universe will now experience accelerated contraction. If the universe is indeed closed and we are alive until the end of the universe, the event known as the Big Crunch, we would experience an unprecedented hellish condition. Initially, the cosmic microwave background radiation, which exists at 2.725 Kelvin throughout the universe, will increase in temperature as the universe contracts and its density rises. The temperature will increase proportionally to the degree of contraction. If the universe shrinks to 1/1000th of its current size, the temperature of the universe would reach 200 degrees, which is about half the temperature of the sun's surface. If we could witness this from Earth, we would see an amazing sight where the entire sky glows as brightly as the sun. As the universe continues to contract to ones of its current size, all the stars in the universe would explode, unable to withstand the extreme temperatures. When the universe contracts to 1 billion of its current size, the temperature would soar to 1 billion Kelvin. surpassing the 900 million K that existed 3 minutes and 46 seconds after the Big Bang. At this stage, all celestial bodies, previously destroyed into atomic forms, would now be broken down into protons and neutrons. The universe would return to a state similar to the time right after the Big Bang when nothing existed. As the universe contracts further, it would reach a state similar to the early moments of the Big Bang. Protons and neutrons, now significantly smaller, would further break down into quarks and leptons. The universe would resemble the initial state of the Big Bang, with positrons, electrons, neutrinos, and photons. Finally, the universe would experience another massive explosion, similar to the Big Bang. This scenario is known as the Big Crunch. Some scholars propose a slightly different theory. Russian astronomer George Gamow, who developed the Big Bang theory by expanding on Hubble's theory of an expanding universe, suggested the Big Bounce theory. According to this theory, the universe contracts to a state similar to the early Big Bang, but never reaches the singularity. Instead, it explodes again, just before reaching the singularity. In simple terms, while both scenarios involve the universe expanding and contracting, the Big Crunch suggests that one universe contracts completely, leading to the birth of a new universe. In contrast, the Big Bounce suggests that the same universe goes through cycles of expansion and contraction. Though there's no way to prove it, if our universe were a closed universe, it would mean there is no true end, just a continuous cycle. However, recent research indicates that the possibility of our universe being closed is almost zero. If the universe were closed, its expansion rate would gradually slow down. However, observations of type Ia supernovae, which serve as cosmic markers, show that the universe is actually accelerating in its expansion. As a result, scientists are now exploring other forms of the universe to determine its ultimate fate. Next, the second open universe scenario occurs when the force of the universe's expansion is stronger than the gravitational force between matter. In other words, the universe's expansion is overwhelmingly strong, causing the universe to continue expanding indefinitely. Unlike the processes in a closed universe, the opposite happens here. As the universe continues to expand, its density becomes infinitely small, and unlike the closed universe, the temperature of the universe, which was at 2.725 K, starts to decrease. As a long time passes, the universe expands to the point where you cannot find any celestial bodies in the sky other than yourself, and the universe is on the verge of absolute zero, 0 K. The last stars burn out all the remaining hydrogen and helium, eventually extinguishing and transforming into one of the forms: neutron stars, white dwarfs, or black holes. Black holes begin to engulf other celestial bodies along with any remaining gas and dust. And after a nearly eternal time of 100 years, black holes evaporate through Hawking radiation, and the fundamental particles that make up matter, protons and neutrons, also decay. Although some remaining particles and radiation still exist in the universe, they too quickly disperse due to the immense expansion speed, effectively leaving the universe empty. At this point, the universe, where no celestial bodies exist or can be created, is practically dead. We call this scenario the Big Freeze. The Big Freeze theory is currently the most widely supported end of the universe scenario. Based on evidence of the universe's accelerating expansion, it is believed that our universe is an open universe and will face thermal death. However, experiencing the Big Freeze firsthand would require an immense amount of time. To reach this state, the universe would need to be at a point where no celestial bodies can be found beyond our Earth. Even 7.8 billion years from now, it is certain that many stars will still be present in our universe. Even if we find a way to settle on a new planet beyond Earth or develop technology to survive in the universe, we cannot prevent the thermal death of the universe, the Big Freeze. Just thinking about it is terrifying. But in an open universe, something even more severe could happen. This is the Big Rip, where all particles in the universe, even space-time itself, are torn apart. The Big Freeze hypothesizes that as the universe continues to expand, the distance between celestial bodies increases, preventing new stars from forming and eventually returning all particles to their primordial state. But what if the expansion speed of the universe becomes much faster than the Big Freeze? To put it simply, imagine pulling a common orange rubber band. Initially, the rubber band stretches as much as you pull it. But if you keep pulling beyond its limit, tiny gaps form, and eventually it snaps. Similarly, our universe would expand initially, but once it surpasses a certain limit, even space itself would tear apart. This big rip depends on the properties of dark energy, which are still not fully understood. Dark energy makes up about 69% of our universe, a substantial amount. As the universe expands, the density of ordinary matter and dark matter decreases faster than the density of dark energy. As a result, the force of dark energy driving the universe's expansion becomes stronger than the contribution of dark matter to the universe's contraction. Moreover, when the universe's size doubles, the density of dark energy remains almost unchanged. If dark energy is indeed driving the expansion of our universe will expand exponentially with time, reaching incredibly high speeds. As the expansion speed continues to increase, it will surpass the point where the universe can maintain its structure, leading to a future where everything, including Earth, the Sun, atoms, protons, and electrons, is torn apart. It would be the most catastrophic and brutal end among the possible fates of our universe. Fortunately, we have yet to prove that dark energy is causing the universe's expansion, and the idea that our universe will reach such a rapid expansion speed remains speculative. However, humans have always evolved by making the seemingly impossible possible. 4 million years ago, no one could have predicted that the human species would dominate this Earth. Therefore, as we wait for the universe's end, which is tens of billions, if not hundreds of billions, of years away, humanity will undoubtedly find a way to overcome this crisis. This has been a segment of Armchair Science.